Hello. Today, let's talk about the fully numerical computation of vibrational properties of small molecules. My name is Jeff Woodford. I'm a professor of chemistry at Missouri Western State University. First, let's talk a little bit about the equation that we're going to solve, and that is the time-independent Schrödinger equation. In this equation, h hat is the Hamiltonian operator, psi is the wave function, E is the total energy, and psi, again, here's the wave function. The h hat operator has two parts, T and V. T is the kinetic energy operator, V is the potential energy operator. So solving the Schrödinger equation yields the wave function for the particle. Now, wait a minute, a particle is a wave? Well, yes and no, but that's a subject for another talk. So, a molecule has several different degrees of freedom, and each degree of freedom has its own associated Schrödinger equation. So for example, the translational Schrödinger equation is here. The vibrational Schrödinger equation is here. The rotational Schrödinger equation is here. And the electronic Schrödinger equation is here. For today's talk, we're going to focus on the vibrational Schrödinger equation here. Now, so how do we solve this Schrödinger equation? So the traditional way has been to use the harmonic oscillator approximation. In this approximation, it is assumed that the potential energy is quadratic in the displacement of the oscillator. V of x is assumed to have the form 1/2 kx squared. So this function is substituted into the Schrödinger equation here. We then have a differential equation that can be solved exactly. So the big pro of this approach is that it can be solved exactly. We have exact analytic solutions for this problem. The big downside, however, is that it does not correspond to a real vibration. So on the right side here, we have a diagram of the potential energy of a typical diatomic molecule. The thick line here corresponds to the harmonic approximation of a quadratic potential energy. The thin line here refers to a potential energy that more closely resembles a real diatomic molecule. You see that down here, if the energy is low, or the bond is not vibrating very much, then the two curves substantially overlap. But once you start getting to higher and higher energies, the two curves diverge significantly. Furthermore, there are plenty of examples of molecules in which even at low energies, the two curves do not overlap all that much. And so the harmonic oscillator is a great model to start with. However, it does have some serious flaws. So one obvious question you might ask is that, well, why not still just continue to work with the harmonic oscillator, right? Since we have this nice, elegant analytical solution, why not just come up with some corrections to it instead of trying to compute the Schrödinger equation numerically? Well, there's two big reasons for this. For very high-level corrections, if you want, for example, very highly accurate energies, these corrections can be almost as consuming in time and in resources as trying to solve the problem fully numerically anyway. So if we're going to have to go through the effort of applying these corrections that take a lot of time, why not start from the original equation anyway? And the second big reason is that if we abandon the harmonic oscillator, it permits a greater class of problems to be solved, and we'll see that later. So, what is one numerical approach to solving the vibrational Schrödinger equation? A very common approach is the vibrational self-consistent field method. This method has been around for a little while. In this method, a vibration is displaced by n points along its normal mode, along the course of its vibration, and the energy is calculated at each point. The vibrational wave function is then expanded in a set of n trial basis functions as follows. Typically, these basis functions are Gaussian type, since the exact harmonic oscillator solutions are also Gaussian type. Therefore, the Schrödinger equation turns into this equation, which is a matrix eigenvalue equation. These two terms here become matrices, and this entire equation here is a matrix eigenvalue problem. If we find the eigenvalues and eigenfunctions, that gives us the wave functions and the energies. Now, this method is not fully numerical because it still relies on the choice of basis functions here. All right? So another approach is the Fourier grid Hamiltonian approach, which has also been around for a little while. In this approach, the wave function is gridded into a discrete set of points. The continuous operations on continuous functions are then translated into their discrete counterparts, so that an operation on a function turns into a matrix multiplication on a vector. This relies on the Fourier transform representation of the Dirac delta function expressed here. So any function can be represented as the integration of the function with the Dirac delta function. So therefore, I can then represent the Dirac delta function itself as a matrix. I take psi, my wave function, and I represent it on a uniform grid of length L that consists of n points. Here, n is chosen to be odd to make sure that we have real solutions to our problem. We then express our continuous variables, x and k, as their discrete counterparts. We then represent this function in this way. We turn integrals into discrete sums, continuous variables into their discrete counterparts. We then wind up with a matrix vector representation of this function. The left side is a vector that corresponds to the function evaluated at the j grid points from 0 to n. The right side turns into a vector of the function represented in grid points from 0 to n. And in between, we have a matrix that's supposed to represent the transformation of this function into this function. However, we see that since they're the same function, this matrix must correspond to the unit matrix, and it does. So the matrix representation of the Dirac delta function is the unit matrix. We can do the same thing for first derivative operators and for second derivative operators. Here, the first derivative operator is transformed into a matrix representation as follows. The second derivative operator is transformed into its matrix representation as follows. I have called these matrices B and C. We're going to need the C matrix for the second derivative, which appears in the Schrodinger equation. All right, so when we do this, the Hamiltonian operator turns into this matrix, and the Schrodinger equation turns into this matrix eigenvalue problem. So, the first trial case we considered was to simply use the harmonic oscillator, since the exact solutions are known. So using the parameters for H2 as follows, the exact solution is n plus a half times h bar omega, where omega, using the parameters for H2, is 0.02 atomic units. The FGH solution, so the Fourier grid Hamiltonian solution, turns out to follow exactly the results of the harmonic oscillator exact solution, where the first value is n equals 0, or 1/2 times h bar, which is 1, times omega, which is 0.02, which gives us 0.01, and 0.03, and 0.05. These are the exact solutions. These turned out pretty good. So since the analytical solution worked pretty well, we thought we'd try some actual molecules. So we're going to take a look at these 5 molecules: N2, CO, Li2, HF, and H2. These molecules were optimized at the CCSDT OG CCP VQZ level. This is an electronic structure method that is extremely high accuracy. So any errors are associated with these calculations are probably not due to the level of theory chosen here. So in these calculations, I'm going to compare the VSEF method with either 8 or 16 points. I'm going to compare that to the FGH method. For the purpose of our comparisons, what I did was I fit the Morse potential to the potential energy points that we got. We did this because we wanted to be able to sample along the Morse potential for the number of points that we needed in order to generate these comparisons. Let's first do N2. N2, the harmonic oscillator value is 2354, the experimental value is 2330, the FGH value gives us 2329 at 11 points. It takes 16 points of the VSCF method to reach an accuracy that is even still not quite as good as the FGH method. So with N2, with the FGH method, we get better accuracy at less cost in terms of energy evaluations. That's pretty good. Now let's take a look at CO. For CO, the experimental value is 2143. Neither the FGH or the VSCF method were spot on, but the FGH method, again, got closer. It got to 2138 wave numbers. The VSCF method, after 16 points, got to 2134. Again, we got better agreement at a lower cost for this molecule. So we were thinking we were doing pretty good after we got these two results. The next one is a little more challenging. It was dilithium, Li2. Okay, the harmonic result is 346. Just coincidentally, it turned out that the experimental result and the harmonic result turned out to be the same. This is because dilithium has a very long bond, so the potential energy is extremely shallow. So, since the potential energy is so shallow, that means that it is approximately harmonic for a wide range of displacements. So the harmonic actually turned out to be pretty good. The FGH method got to 340, here with only 9 points. The VSCF method got to 341, one better than the FGH method, after 16 points. Still, this is pretty good. So after these three molecules, we were feeling pretty good about our results. The next two, however, are particularly challenging for us. The next one we're going to take a look at is HF. So the experimental value is 3961. The FGH method got 4028. That's pretty far off. And the VSCF method got it almost spot on at 3965. So, and as you can see from the trend with N, it was unlikely that by adding more points, we're going to get substantially closer to the experimental value. So there's something wrong going on here with these calculations. Then the next one was even harder still. This was H2. Okay, so the harmonic value is 4401. The experimental value is 4161. The FGH method got 4319. It's pretty high. And the VSCF method got pretty close at 4158. So these past two cases, H2 and HF, are relatively light compared to the other molecules we have seen. And I think that is one key as to why these two systems are not working very well so far. We're continuing to look at it, though. I think there are two main sources of errors. Is that so the error due to the Kerr fitting, remember I had to fit them to the Morse potential, so maybe that was off by too much. And then due to the grid spacing, perhaps I should choose a smaller grid spacing for these. Now, for future work with these, we're going to be looking at molecular vibrations in terms of internal coordinates. Now, representing everything in terms of x, y, z is very convenient from a mathematical point of view. However, it is typically not how chemists think. Chemists tend to think in terms of internal coordinates, such as bond stretching, angle bending, or dihedral twisting. So the vibrational Schrödinger equation in a general curvilinear coordinate system is as follows. Wow, this is a really complicated equation. J here is the Jacobian matrix, and G here is a type of inverse mass matrix that takes the place of mu that was in the one-dimensional vibrational Schrödinger equation. So here the potential energy part has not changed. What has changed is the kinetic energy part. So if we want to compute derivatives of terms like this, like with the Jacobian and with my G matrix, I'm going to have to use a grid-based approach anyway. So since I'm going to have to resort to grids in order to evaluate these, then I might as well choose a fully gridded numerical approach anyway. And that's what we're going to be working on. So conclusions. This FGH method is a fully numerical method for solving the vibrational Schrodinger equation. No basis functions or no analytical solutions are required. So far, this is working pretty well if the molecule is relatively heavy and the bond is relatively stiff. It is not so good if the molecule is relatively light, and we're continuing to look at why that is. And in future work, we're going to implement the FGH method for internal coordinates as well as for multiple dimensions. And I must acknowledge Mr. Nelson Maxey. He is a BS chemistry student in our department. He has done about 90% of the programming on this project, and so he's been extremely helpful. The Department of Chemistry for all the computational resources I've had access to, and you for your undivided attention. Thank you very much for listening to my presentation.